As we know, engines are very important parts of airplanes. That is where we get the thrust from, and without them, the plane just wouldn't fly. But would you believe that we still don't really understand the effects of engines on the aerodynamics of wings and airplanes? And when you think about it, I guess it isn't that surprising that we don't know, because when you think about the different ways that we test the aerodynamics of airplanes, we're kind of limited. For example, if we put a plane in a wind tunnel, first of all, it needs to be a scale model. And second of all, the engines aren't firing. So the thrust isn't being taken into account. Another way that we can test aerodynamics of airplanes is through real life flights. But again, we are very severely limited in what we can measure. And usually it's just more about the stability of the airplane, both static and dynamic, and also efficiency. So we're kind of left with just CFD, and surprisingly, most of the time the engines aren't even really modeled properly in CFD. Often the flow through isn't even captured, let alone the acceleration of the flow and pushing it out the back. And the reason for this is because it is quite difficult to model this flow. As a result, exactly how an engine affects the aerodynamics of an airplane aren't really known. That means that whenever we are testing different wing configurations, the effects of the engines are kind of ignored. And I can confirm that because in my testing of different airplane configurations and development, particularly in the early phases, the engines are really neglected. But does it make sense to forget about the engines? I mean, would they make much of a difference to the aerodynamics of the airplane anyway? Well, yes, and for a couple of really good logical reasons. The first is that at the very least, we have this big block right under the and even ahead of the wing, which means that the flow has to be redirected. And secondly, the engine itself pulls in air around it, which means that the regions of the wings around the engine will be starved of air, and air from elsewhere now has to rush into this region to take place of the original air that was supposed to be flowing over the wings. That also results in some skewness to the flow. In addition to all of that, the engine then throws air out the back of the nozzle, and that is at really high speeds. The air is now going to change the flow around it too, and depending on what that pressure is, it can either draw more air into that region or push it out. So there are a bunch of reasons why it is very logical to think that an engine will affect a wing's aerodynamics and the rest of the plane too. And then on top of that, there will be major effects to the airplane stability, because now certain regions of the wing are producing more or less lift and more or less drag, which then changes the moments around the airplane. As such, understanding the engine's effects on the flow is a good idea. And that brings us to today's podcast. So today, we are looking at the effects of a turbofan on an airplane's aerodynamics. And this turbofan is operating as well. It's not just a block of mass, but it is actually being modeled as sucking in air and throwing it out the back. And it's really cool how they're actually doing this. We'll get into it in a little bit. So to look at this, we're looking at this paper called Powered Turbofan Effects on Aircraft Aerodynamics at High Lift, a study of the NASA CRM-HL, which is a software. As usual, this is an open access paper, and you can find it in the link below if you're inclined to peruse it yourself. So let's get into it. So these researchers looked at a turbofan and the effects of this on the airplane's aerodynamics, because turbofans are really the most common engine out there. So I mean, sure, small private airplanes often have turboprops, but most people will never fly on these private small planes. Most people fly on regular airliners. So if you look at the amount of work of each type of airplane that it does, by far the turbofan is the workhorse of the aeronautical industry. And these researchers looked at a very complete airplane, by the way, with all the typical high lift flow control devices that you would get on a regular airliner. It has the regular flaps and also the flap track fairings, which are those bits that the flaps actually deploy along at the back of the wing, which gives the wings more camber, greater surface area, and overall much, much more lift. So if you look at a wing that can only really produce a lift coefficient of like, let's say 1.2 without flaps, with flaps, this wing can now get to about 2.0, 2.5, even higher. So flaps make a huge difference to the production of lift of the wing. In addition to the trailing edge flaps, this plane also has the leading edge flaps and the slats and the structures supporting to them. So we can see here in this picture the slats coming through here. And the leading edge slats kind of do the same thing as the trailing edge flaps, but just on the front of the wing. They extend forward and down. That then increases the camber of the wing and the surface area of the wing as well. So they too greatly increase the lift of the wing. And they also potentially increase the amount of flow that comes up over the wing and then keeps the flow attached over the rest of the wing, so you can go to higher angles of attack. So this model is a quite high fidelity model. And just here, I should also say that if you want to learn how to do OpenFOAM, which is a really good CFD software, and it's completely free, but really hard to learn, you can take our course where we go through literally step by step, even how to install all the way to running your own DES simulations. So you can find that course in the link below. Let's get back to this paper though. So to look at how the engines affect the flow over the airplane, the researchers used CFD, and to model the operation of the turbofan, they used two approaches. So these two general approaches can be seen in figure 1. And so why did they use two different approaches? Well, to understand that, let's talk about how a turbofan works. So a turbofan has two general sections. The first is the inner section, the core, and then the second is the outer region, which is just really the fan part. The core is where the fuel is burnt, and while in the fan section no fuel is actually burnt, some of the engine energy from the burning section gets tapped off and then used to power this fan section. So these researchers went to great lengths to actually model the engine performance, because for the inner core section, they literally used thermochemistry to determine how much energy is in the flow, and hence the flow physics. When you start coupling thermochemistry in your simulations, that greatly increases the resources you need, and it gets very complicated very quickly. So for this study, they relied heavily on this first approach, where they looked at just modeling thermochemistry and then the energy coming out of the flow. Then they used a second approach for a couple angles of attack just to see how they affected the results. So let's move on to the simulation validation results and see how well they did, because it's actually quite interesting, this CFD, and you'll see it as we go through why it's so interesting. So table 2 shows the grid convergence study's results. So let's go down to table 2 here. That's table 1. Table 2 is down here. Let's zoom in so we can see a bit better. All right, now we're talking. Okay, so this table 2 is for when the engine had the thermochemistry included. So really the more difficult approach, in my opinion. So in table 2, we see that they tested 3 different levels of fineness, going from coarse all the way to fine. And they really increased the number of cells used between these levels. So I mean, for the coarse mesh, they had 20.8 million cells. Then for the medium mesh, they jumped up to 57 million cells. Then for the fine mesh, they are now at 128 million cells. This alone means that this will be a really good grid convergence independent study, because as we covered in other podcasts, much of the time researchers, when they do grid independent studies, literally just increase the number of cells they need by like 10 or 20%. Then when the results converge, they say, yep, all done. When in reality, that jump of 10 or 20% is nowhere near enough to guarantee that your grid has converged. In this CFD study, on the other hand, these researchers went the whole hog and they more than doubled the number of cells of each refinement. That is really good practice. So in terms of the results, they give the lift, drag, and moment coefficient, which is really nice. That is a very thorough approach. So the moment coefficient is also a good way of telling really how much lift you're producing and drag you're producing across the airplane, because that affects how much the airplane wants to pitch. So it is clear that once they reached the medium mesh, that mesh had converged, because none of the coefficients above this medium mesh changed more than 0.3%. So you can see the lift, drag, and moment coefficients are almost identical when we go to the fine mesh as well. So we can say that this mesh has converged. Now in figure 2, we see the lift and drag information of their simulation. So let's go to figure 2 up here and zoom in a bit more as well. Okay, we can get both of them, that's good. Okay, so from what I can tell, they have actually the experimental results in the green and the CFD results in the red. And from what I can tell, the experimental result was taken at a Reynolds number of 5.5 million, which means that this is obviously not conducted at full scale, but that would be quite impossible. I mean, you can't put a full airplane into a wind tunnel. So for low angles of attack, the lift coefficient, which is in the top figure here, is very, very accurate. I mean, it is bang on the experimental data. You can see that there's a huge overlap between them. It's fantastic. As we get to high angles of attack near stall, the CFD starts to overpredict the lift coefficient, which could be due to the Terminus model that they use in this RAN simulation. It is Spalled-Almaros. However, it could also be because of the engine's performance. Either way, the differences aren't that major when you really consider how good it's getting lower down as well. Now, in terms of the drag polar, the bottom section in figure 2 shows the comparison with the experiments. So again, at low angles of attack, which here is when the drag coefficient is low, the drag polars are very close to the experiments. And as you approach stall, so the higher red squares here, the CFD starts to deviate from the experiments. And this figure indicates that not only is the lift off a little bit at these high angles of attack, but the drag is off a little bit as well. and this is above like 15 degrees or even higher. So in addition to these lift coefficients, they also give the pressure coefficients over the wings in figure 3. And then they compare them to the experimental data. So this is for a 7.05 angle of attack, degrees angle of attack. This is insane because you almost never get this amount of validation data. They have the lift and drag, but now also the pressure plots over the wings. And this is thoroughly done, this validation study. So the different figures in figure 3 correspond to the different locations along the wing. They call them belts, which I guess makes sense because they are strips running from the leading edge to the trailing edge as you go from the root to the wingtip. And they call belt A is the belt closest to the wingtip, the wing root, sorry. So this one here. Then belt H is the one closest to the wingtip, and then all the rest fall in between. So I still can't get over how thorough the validation is though, because they have so much data here, and it's awesome. So to be perfectly honest, there isn't really anything to talk about here because the CFD very closely mimics the experimental results. That's great. That literally means that at this 7.05 degree angle attack, this CFD is pretty much perfect here. But wait, there is more. There's also the pressure coefficients over the wing at 17.5 degree angle attack in figure 4. So here, the CFD is very accurate for the inboard region, so belt A up to about belt F. Then belt G and belt H, which is getting close to the wingtip, the CFD starts to differ from the experiments. That tells us that the flow separation and the physics at the wingtip isn't captured properly by the CFD. This also tells us that when we get to high angle attack, the CFD starts to deviate from experiments because of this reason. The wingtip region isn't really being mimicked properly. That isn't a big deal because it is very, very difficult to CFD a wing accurately in this stall regime though. So it's kind of expected. So from this validation and the grid independent study, I am quite impressed with their CFD, and I would rate it like 9 out of 10. I think we can definitely trust their general flow physics and the forces that they present later on. I mean, the validation showed that the forces and the pressure coefficient plots were bang on for all low angles of attack. And okay, there were some differences at high angles of attack, but that is to be expected, and the low angles of attack were perfect. It is rare that you can say that about CFD. So they also say that their Y plus is below 1 as well. So I think the CFD is really good. With that, let's move on to the results now. So in figure 8, if we scroll down here we go. Let's zoom in a little bit as well. Here we go. Figure 8, we see the pressure coefficient distribution over the suction surface, and this is all for CFD now. And the suction surface is the top row, and then the pressure coefficients over the pressure surface over the bottom row here. So they also give some streamlines showing where some of the flow is going. And overall, the engine definitely seems to affect the flow over the suction surface, so this top region here. And we can see that the streamlines just downstream constantly curve towards the fuselage. So to begin with, they're all sort of flowing at some sort of angle, and now all of a sudden they just sort of shoot off more towards the fuselage. And this is kind of regardless of the angle of attack as well. Alternatively, on the pressure side, so this bottom row here, as the angle of attack increases, more and more of the flow curves into the downstream region of the engine. So you can see here at this low angle attack, the flow is quite straight as it goes along, and then as we get to high angle attack, it starts to get sucked in behind the engine. And the authors say that in this region, the pylon, which is that thing that connects the engine to the wing, creates vortices, and perhaps the low pressure in this region from these vortices pulls the flow into this region. Another really interesting thing is that at 18 degrees on the suction side, most of the leading edge is experiencing flow separation. But just downstream of the engine, the flow is still attached. So you can see here, there's very low pressure here, but just here, just behind the engine, if I zoom in, it will be a bit easier to see, we have flow attachment still, and the streamlines are at a different angle as well. So this means that the engine and the pylons are delaying the stall in this localized region. So they are affecting the flow over the wing. So in figure 9, if we go down to figure 9 here, let's zoom in a bit. We have the skin friction coefficient distribution over the wing's suction and pressure sides. Again, the suction side is on the top row, the bottom row is the pressure side. So one thing that I should point out is that at 6 degrees, the suction side, I'm pretty sure is wrong. It's not the right figure. It's actually accidentally just a copy of the suction surface at 18 degrees. So let's ignore that figure there, but let's look at the rest of the figures. So at 18 degrees, which is the right figure here, there is one very large region of low skin friction here, just behind the engine. Looking at the corresponding pressure coefficient plot in figure 8, there are streamlines tracing towards the fuselage in this region. You also say that this is a vortex that is actually being created by the cutout of the leading edge slat to accommodate the engine. So literally this cutout here, where the engine is attached to, that's creating vortices and it's coming up over. We'll see a little bit later if that is true or not. There's also some more flow phys which illustrates what's going on here a bit better. Anyway, this vortex is inducing very low skin friction in this region. It's also interesting how it isn't actually the engine itself, but the accommodation of the engine into the wing that creates this vortex. So it's that additional component as well. Now for the pressure surface, if we zoom into figure 9C, which is this one here, we see the streamlines on the surface. And remember how I was saying that in the downstream region of the engine, a lot of the flow is being drawn into it. Well, we see the exact same thing happening here where these streamlines really get sucked in here. And interestingly, the skin friction is much higher in this region than the surrounding zones. That tells us that the flow migrating into this region is faster moving near the wall. The boundary layer may be more turbulent or maybe something, I don't know, but it's probably more turbulent at the very least. The velocity near the wall is much higher than the surrounding regions. So in figure 10, we have a really cool figure where we see something really cool. We have these criterion shown here, these isosurfaces, and these effectively just show where vortices are being created. And this is what I was talking about earlier, where we can determine whether this vortex is really coming from that slat or not. And we can see a bunch of these vortices forming and of all different sizes. To begin with, there is quite a lot of small ones that form because of the connecting rods, etc., from the leading edge slat. So you can see all these tiny little ones being formed here. That's from this leading edge slat and how it connects to the wing itself, all these little hinges. But we can also see the vortices from the cutout, as we mentioned earlier. So there are some vortices coming from the cutout here, and that's true, that is coming here. But there's also one huge one originating from this nacelle, and then it goes over the suction surface. So you can see in all these three figures, you have this big vortex forming and it gets sucked over the top of the wing. So for some reason, this huge vortex forms around halfway down the outside of the engine. Then it flips over to the suction surface, and it even occurs at low angles of attack, but it's just much smaller. So this alone is responsible for much of the flow physics we saw in that area earlier, not just the vortices from that cutout in the slat. Also, interestingly, at 18 degrees, if we zoom into the inlet a little bit more, here we go, we see that a major vortex is forming in the mouth here compared to the other regions where there is no vortex forming. That is because the flow is separating over the inlet edge and creating the vortex here, and that's because the engine is now at quite a high angle of attack as well with the rest of the airplane. So we're getting flow separation here, and that's going to reduce the performance of the engine a little bit as well. So moving on to figure 11, we see the surface streamlines over the engines. And at 6 degrees and 12 degrees, we have a few different images to show here. The top row is for 6 degrees and the bottom row is for 12 degrees. The left column is for the inboard part of the engine, so the inside face. The middle column is for the outboard region, so the outside face. And the right column is for on top looking down. So looking at the geometry, we immediately see the cause of that massive vortex we saw earlier on the inside of the engine, which then flips over to the top of the wing. The reason why this vortex forms is because there is an actual fin on the engine. If we zoom in here on the inside of the engine, we see this fin here and also on top here. So that fin there is creating that massive vortex. So the streamlines we can see are curving towards it, not only from the top into it, but also from underneath up into it. And when it hits that fin, it then rolls up into this massive vortex. So it's quite interesting how the flow over the engine on the outside moves up, and it consistently wants to go from the bottom to the top of the engine. So it goes bottom all the way up. And also this is for 6 degrees too. So I wonder how you'd be able to straighten up, because this curvature would increase the vortices being formed on this engine. And if you could straighten the flow, you'd probably get fewer vortices and also reduce the effects on the engine. Maybe that's what this fin is supposed to do a little bit, perhaps straighten the flow in some sense. So let's move on now to figure 13, where we see some really cool cut planes through the engine itself. Here we go. And let's zoom in a little bit. Okay, so one thing that these planes really show is that for the 6 degrees and 12 degree situations, the flow is coming up at an angle to the engine, so you can see how much it goes up. Looking at the inlet though inside, it does a really, really good job of straightening the flow into the engine. And that's why when we saw earlier when we had 80-degree angle attack, the flow separated over the inlet lip. That's because the flow was just at too great angle attack. And then the inlet couldn't really straighten the flow into the rest of the engine very easily. But here you can see, for example, in figure 13E, if I scroll down to figure 13E, let's zoom out a bit, that the engine is kind of flirting with making the flow separate over the wing because it's providing an upstream blockage, so just here, and that redirects the flow a little, and the wing is kind of starved of flow. So you can see here, the streamlines come in, zoom over the top, and now this wing is not really seeing this clean flow. It's more seeing a dirtier flow, I guess you could say. That means that the engine might also start to cause premature stall at this part of the wing. So now let's look at figure 15 because we see a pretty cool breakdown of how much drag, but also how much thrust each component of the airplane is producing. So it might seem strange that I'm saying thrust because only really the engine should be producing thrust, but we're going to talk about how this is possible. And we have 6 degrees and 12 degrees in dark blue and light blue respectively. So the trends stay pretty much the same regardless of the angle of attack as expected. The wings, wing flaps, and fuselage are producing drag. But interestingly, the wing slat now produces thrust, as you can see here. So that is a little strange to think about because first, we naturally expect these things to produce drag. But let's consider if it's possible that a passive part of the airplane can produce thrust, not the engine, but just another part of the airplane. So when it comes to drag of an airplane, there are 4 main components. There is the skin friction drag, the pressure drag, induced drag, and wave drag. Often you will hear different names like interference drag, for example, but those names are really just combinations of these different ways that are producing drag. So for any passive object, you can't really get negative induced drag. In other words, you can't really produce thrust through the induced drag mechanism. Whenever you have that mechanism, it will always produce induced drag. Looking at the mathematics of it, induced drag is to do with how quickly the lift tapers off as you reach the wing tip. So there is no way to get a negative value and hence produce lift. If you really try, I guess you could maybe utilize the structures being created and then create some sort of thrust out of them. But at its core, induced drag is always a drag. And if actually on our YouTube channel, if you go to a video called Aero Fundamentals number 30, Induced Drag Explained, I go through this type of drag so you can understand it better as well. Now moving on to wave drag, likewise, that can only ever be drag as well. You can't really create thrust out of the mechanism that creates wave drag. Now we come to pressure drag and skin friction drag. These 2 types of drag can actually be manipulated to produce thrust under certain circumstances. So let's talk about the pressure drag first. Pressure drag is nothing other than the imbalance of pressure upstream and downstream on faces. That imbalance creates a force. So imagine you have a piece of paper and it's vertically aligned with the flow, so the flow is hitting straight onto it and there's a wake behind it. The front face, let's say, is experiencing a pressure of 100 pascals and the rear face is experiencing 0 pascals. Well, in that case, there is a net difference of 100 pascals. And we know that pressure is simply a force over an area. So if you were to multiply this pressure difference by the area of the sheet of paper, you get now a force. That force is pushing the paper back. That is pressure drag in a nutshell. And on our YouTube channel, there's a video called Aero Fundamentals number 18, Airfoil Drag Explained. I go through this in more detail as well as the skin friction drag. So knowing that the pressure drag is nothing other than an imbalance in pressures on the upstream and downstream surfaces, if you flip the imbalance such that the upstream face is at a lower pressure than the downstream face, then all of a sudden you have thrust being produced. So in this case, you can actually use the idea of pressure drag to create thrust. So this component of drag doesn't always have to be drag. It can sometimes be thrust. And likewise, skin friction drag isn't always producing drag either. In fact, skin friction drag is nothing other than the friction that arises when fluid flows over a surface. There is resistance to that motion, but what if the fluid was traveling in the opposite direction? Now all of a sudden, the resistance to that motion is in the direction of travel, and hence you are now producing thrust. So the two components of drag, pressure drag, and friction drag don't always have to be drag, but the mechanisms used to create these components of drag can actually be used to create thrust now. And that is what we are getting here in figure 15, where the slat is actually producing thrust. So how could it be doing that? Well, looking back at figure 9, we actually have all the information we need. So we have the skin friction coefficient in figure 9 as I'll scroll up here. Here we go. Okay. We can see that under the slat, so under here, we start to get some negative values and also even 0 and negative values here. That alone would be enough to make this slat produce some thrust, because if we scroll up to figure 8, we get an even better idea as to how we're producing thrust. So we see that the upstream surface, so the upper surface here, is very blue. That means that we have a very low pressure on this upper surface here. Now on the downstream surface, which is under the wing, we get a relatively high pressure here. That means that there is now high pressure on the back face and low pressure on the front face of this slat, which results in a pressure imbalance pushing the slat forward. So in this particular case, I would say that most of the thrust that the slat is producing is coming from the pressure drag being reversed here locally, and some of the thrust perhaps from the skin friction drag, but most of it from the pressure drag. And that makes sense because as angle of attack increases, we see that the slat produces more and more thrust. And that agrees if I go down to that figure again. So we see more and more thrust is being produced as we go from 6 degrees to 12 degrees. And that makes sense with what we've been seeing in figure 8 here. If I scroll back up, we get more and more low pressure on that slat here as we increase angle of attack. So the forward-facing surface becomes lower and lower pressure, and that increases the thrust. And that feeds into the trend that we are seeing here. So that is a pretty cool development. So looking at figure 17, we see a similar effect where for some of the components of the actual nacelle, there is thrust being produced as well. So figure 17 is down here. Let me zoom in. There we go. Okay. So for the intake, for example, it is producing a lot of thrust. And while the actual structure connecting the engine to the wing, this pylon, is producing a lot of drag. So part of the engine is beneficial for reducing the drag of the airplane, at least directly, while other parts are not. And the engine also has indirect effects as well, as we've seen from the vortex coming up. So with that, we come to the end of this podcast. And I was really surprised with some of the results, including just how big some of the vortices coming off the engine were, and how much they affected the wing, the flow over the wing, as well as some of these regions producing thrust, which we've seen here. So if you want to learn how to do OpenFOAM, which is a completely free and really good CFD software, take our course in the link below. We go through step by step, literally how to even install it, all the way to running your own DES simulations. We also have other CFD courses that take you through the basics all the way through to more advanced items like sliding meshes. And if you want to make your experiments more accurate, then, and if you didn't really know already, your experiments probably have a 2 to 4% error in them, and you didn't even know it. The reason is because the density of air changes throughout the day, and in the link below, we have done the math showing just how much it changes and how it affects your results. So to get rid of this error, we make an instrument called the Atmosphere Hawk, and you can find that in the link below. And with that, we come to the end of this podcast. So I'll see you next one. Peace out, amigos.